Hello everyone. In this video, we are going to look at a left wall following robot in CoppeliaSim. And this is done with the PID controller. So here we have the Pioneer P3DX robot, and we have this scene, which is a room with wall in the middle. So let's go ahead and look at the behavior. The goal is to follow the left wall of the robot and then keep the distance from the wall at a fixed number. And initially that distance is not exactly the desired distance. So you see the robot moves a little bit to the left, and then once it reaches the desired distance, it kind of settles down. Now there is a little bit oscillation at the corners, and it's an underdamped behavior, but once it settles, it kind of goes straight, and it can do this back and back and back to back and no problem. So how does it achieve that here? Although it looks like, yeah, it's very simple, but actually you need a good control to make it happen. So here is the script that I have written for it, and I'm going to share it with you under video description if you want to see. So it's with PID control, and there is a filter on the derivative, and there is also obstacle. So you make sure also you don't hit into anything. So how does it work? We get the sim, we get the robot handle, we read in all of the 16 sensors, although we are not using necessarily all of them. And if you remember, the sensors on the Pioneer robot is I showed you in one of the previous video. Let me show you also here. So this is the map of the sensors, right? So this is the front, back, and left and right. So the goal is to use these guys on the left side, and some of them are the front, okay? So these are the sensors we are going to use here. We get the handles for the left and the right motor, and we set up some min and max distance for or max distance and no detection distance for the ultrasonic sensors, which are 0.05 and 0.8. We set the speed, the average speed of the centroid, which is 2. You can change that, any of these parameters you can change. A max wheel velocity of 6 and a min of 0.06. The max, we don't want to go faster than that. The min, we set it such that if the speed of any wheel goes less than this, we automatically basically do a dead zone and set it to this number. So we do some kind of saturation here. So no velocity of any wheel should go below this, because if it does, it might not be enough to, at least in our simulation, to move properly forward. And then this is the target distance from the walls, 0.35. Feel free to make it smaller or bigger, depending on how you want to keep the distance to the walls. These are the gains of the PID controller, 1.2, 0.2, and 0.4. And here we also have some maximum for the integral. This is the anti-windup. If you just watch my channel right before this video, I published a video on anti-windup, because we don't want the integral of the error to be very big, okay? So here we have a max integral, and the same thing for max steering. Then the PID, as I said, has a filter. So it's PID plus low pass filter. This is the filter coefficient. And then the front brake distance and the front slow distance are these numbers. So once you reach within this distance of any object, you're going to slow down. Once you reach within this distance, you're going to brake. So here we're going to start everything. We're going to read the sensors, and then you can see that basically here we are going to get the object position. These are the positions of the sensors on the robot, basically. And once we get them, if it's the position of them, number 2 is bigger than 0.01, then we insert them on the left sensors. If it's bigger than negative 0.01, we insert them into front sensors. Or you could just give them an index for them. But here we are doing it based on the X and Y of the sensors around the center of the robot. So as I said, the goal is to just focus on the left sensors and on the front sensors. So here we are doing it again based on X and Y of these locations around the center. Or we could say, hey, if they are like 0, 1, 14, 15, they are the left. And if they are 2, 3, 4, 5, something like that, they are the front. But here it's a different way of putting them under left and front sensors. Now here we have this function that reads the distances from your proximity sensors. The command you can see, sim read proximity sensor. And then if the result is bigger than 0, which means something is read through the sensors, and the distance is less than no detection sensor, which in this case we set it to 0.8, what's going to happen here? Then we're going to set it, if that's the case, then now we check it against the maximum. So here we assume that the distance is below 0.8. This is the point beyond which nothing can be read. And then now we compare it against 0.05, okay? And actually this should be minimum, not maximum. This one here should be called minimum, not maximum. I have to fix that. And then we compare it against here, and we set the proper distance based on the no detection or based on the actual distance. So here we are basically putting a cap on the distance that you read from the sensors. Then here we calculate the left distance, because remember we have several sensors on the left, so you are basically looking at an average of them. As you can see, you get the average of the left side sensors. Okay, so this is your actual distance. You have to compare it against this number 0.35 to get your error. The other thing you need to do is to look at the minimum distance. Okay, this is for obstacle avoidance. And again, here you're going to look at the sensors on the front. Now here, look at the main function, the actuation function. You get the time, and you need to subtract it from the previous time to get your basically time step. You need this time step for performing derivative and integral operations or integrations in the PID. Okay, and if it's less, if it becomes negative, it shouldn't be, but if it does, we're gonna set it to 0.001. Okay, so now we get our left and front distance from those functions. We calculate the error as the difference between target distance, that 0.35, and the left distance, which we got from the function. Then we update our integral term. Okay, this is the accumulation of error over time. And look what we do. Here, whatever it was, we add to it e times dt. And then we're going to use the max and min functions against the max integral and the negative min integral to do the anti-wind up. So this part here is, we call it the integral clamping anti-wind up. Okay, so here we are doing that, and then here we perform a derivative. This is raw derivative, which is current value minus previous one over dt. And then we use this coefficient that we had, and we add the low pass filter to the derivative to get the derivative plus filter. So this derivative here is the one that does have the filter to it, as you can see. And then we add all of the terms together. So this is the actual PID, as you can see here, right? So this is the PID. And you can see all three gains. And then again, here I compare it against this maximum and negative maximum steering value to apply threshold on it. So this is a saturation, right? Remember, you have a saturation in your physical system, so this is simulating that. And then I'm gonna add and subtract this omega command, you might call it, or steering, to the velocity of the centroid to give me the commands for the left and the right. Here you perform the obstacle avoidance override. So if they are less than the break distance, okay, what you do is you apply 0.6 of that V naught and negative 0.6 of the V naught to the left and right. So what does this do? It is gonna make it spin in place, right? Because the velocities of the two wheels are positive, negative of each other. Otherwise, you make them 0.35 and 0.75 of what they were. So here you're just slowing down. And then once you take care of that slowing down and braking, if it's within those distances, then you come and look at the velocity clamps and the dead zone. And so if any number is, any of these commands is below this guy here, you're going to what? You're going to set it to some minimum value here, right? So they don't go below that. And finally, once you set your final commands, you're going to use the set joint target velocity for the left and right, pass them to it, and then here you're going to do some updates, and your cleanup does not really do much here, okay? So you can even get rid of it if you want to. And if you're saying, what kind of assignment is this? There are 3 things on the left, 3 things on the right. That's exactly an assignment of multivariables to multivariables. So you set the current error, you replace the previous one with the current one, you replace the previous derivative with the current derivative, and you replace the previous time with the current time, okay? So this is a multi-assignment or multi-variable assignment. Okay, so 3 variables are assigned at the exact same time here. So the only thing that I don't like is this guy here. So let me go ahead and make it a min distance, because that's what it should be. And the only line that had that variable is here in line 55. So all you need to do is to change these two to min distance. And the rest of it should be relatively clean and good. So here, let's say integral clamping anti-wind up added. Okay, and there is a derivative filter and there is obstacle override. So this is a very stable code in terms of making sure no impact happens. If the signal is noisy, it takes care of that. If there is saturation, it takes care of that. So that's why you see that it is actually doing the job properly. Okay, so even a simple left wall following needs to be done properly so you can get the proper performance. So I'm going to share all of this code with you under video description. Feel free to work with it. Maybe you want to modify it to do a right wall following or anything. Maybe you want to create your own maze and have this robot follow that. But this is the essence of a left wall following. And again, right wall following is exactly the same, except use the right side sensors instead of the left. And you might start it on the right side. So you start maybe on this side and go this way. So hopefully the video was useful to you, and I'm going to see you in the next video. Thank you.